So deflection of simply supported beam carrying a point load at the center. A simply supported beam AB of length L and carrying a point load W at the center is shown in the figure. So simply supported beam, load is W, it is acting at center. The length is L. As the load is symmetrically applied, the reaction RA and RB will be equal. Also, the maximum deflection will be at the center, RA equal to RB equal to W by 2. So, the first point is the reaction will be equally distributed as the load is at the center. So, as it is W, W by 2, RA, R is W by 2, RB is W by 2. Then the maximum deflection will be at the center. So, Y max will be at the center. Consider a section XX at a distance of x from the left hand side. Now our aim is to find this deflection y max. What is the maximum deflection and what are the slopes theta and theta v? We will find using the Macaulay's method or a double integration method. Now in this the procedure is, first of all we have to consider a section XX at a distance of x from the left hand side. The bending moment of the section will be given by mxx equal to ra into x. So we need to cut a section in this way at a distance of x from A. So at this point we need to calculate the moment. So if we forget right side we have force Ra. So Ra into x is the moment. So mxx equal to Ra into x. But we know that from differential equation m equal to Ei d square y by dx square. So we have equated both of them. So therefore Ra into x equal to Ei d square y by dx square. Therefore, but Ra we know that Ra equal to W by 2. So Wx by 2 equal to Ei d square y by dx square. Let it be equation 1. So integrating this equation, we will get the slope equation. How? So first of all, let us integrate it. So it will become Wx square by 4 and it will become dy by dx and the constant will come. So to find this constant C1, what you are doing, the value of C1 can be obtained by applying boundary condition for slope. We have to apply boundary condition for slopes. What are the boundary condition for slope? See here, at A, slope is theta A, at B, slope is theta B, at center, there is no slope, theta equal to 0, dy by dx equal to 0. So at x equal to L by 2, dy by dx equal to 0. See here. So applying the boundary condition at x equal to L by 2, dy by dx equal to 0, substituting these values in equation 2, that means in this equation, we will get C1. So Ei into 0 minus WL by 2 whole square by 4 plus C1 equal to 0. So C1 we got as WL square by 16. So substitute C1 equal to WL square by 16 in equation 2, we will get a slope equation. So substitute in this equation 2 C1 value. Then the equation is slope equation. Now to find theta and theta B, this theta A and theta B, what we have to do, we need to substitute x equal to 0 to find theta A. So x equal to 0 in equation 3, this equation, slope equation, if we substitute, we will get C. We have substituted x equal to 0, then theta is theta A, dy by dx at A equal to minus WL square by 16 EA. So theta A equal to theta B equal to minus WL square by 16 EA because the load is applied symmetrically. Therefore, both the slopes are equal. To find deflection, now our aim is to find the deflection, maximum deflection. So for this, how to find, integrate, first of all, we need to integrate the slope equation, that is equation number 3. We need to integrate this equation. Then we'll get Ei by minus this term, and plus C2 will come extra. Now how to find this C2? Apply the boundary conditions. See here, at x equal to 0, there is no deflection. So x equal to 0, y equal to 0. We can apply that boundary condition. If you see here at x equal to L by 2, y is y max, at x equal to L also, y equal to 0. Let us apply this boundary equation. Then we will get in where we need to apply. Applying boundary condition in this equation, we can find C2. So C2 equal to 0. Now substitute this C2 equal to 0 in equation 4. In this equation, yeah, then we will get this equation. This is known as deflection equation. Let it be 5, equation number 5. Then to find maximum deflection, substitute x equal to L by 2 in equation number 5. So Ei y max minus, so what we need to do, at x equal to L by 2, y equal to y max. Therefore, I am substituting y in place of y max, and here instead of x, L by 2. Then if I solve it, I will get y max equal to minus WL cube by 48 EI. That is the maximum deflection. Same we can do for a simply supported beam subjected to UDL also. But what is the difference means here RA we will get as WL by 2, RB WL by 2, because how to convert UDL to point load? So load into span. So load is W, span is L. Therefore load is WL. So WL by 2, WL by 2. See here, m equal to ei d square y by d square. First of all, we have taken the differential equation. Then what we have done, we have taken the moment. We have taken a section. So x, a distance of x from A. At this point, we need the moment. Forget right side. Left side, we have two forces. That is point load and UDL. Point load RA into x, and UDL is also there here. UDL is WX into x by 2. So W is the load, X is the span. WX is the total load into x by 2 because it is acting at the center. So instead of RA, we can substitute WL by 2. So integrating this equation, we will get in terms of C1, how to find same procedure now. To find C1, we have applied the boundary condition. What is the boundary condition? X equal to L by 2, dy by dx equal to 0. When we apply this boundary condition, we got C1 value as WL cube by 24. Now substituting this C1 value in equation 2, in this equation, we can find the slope equation. You can get the slope equation. Now to find theta A, theta B, simply substitute x equal to 0, theta equal to theta A. See here, at x equal to 0, slope is theta. X equal to 0, that means support A. The next slope. So we got theta as minus WL cube by 24 EI, which is equal to theta B because load is applied symmetrically. Now integrating equation 3, that is slope equation, we will get the deflection equation. But here C2 constant we have got. To find this constant, we will apply x equal to 0, y equal to 0. So substitute x equal to 0, y equal to 0 here, we will get C2 as 0. C2 we got as 0. Substituting C2 value in equation 4, what we get is this one, deflection equation. To calculate y max, substitute x equal to L by 2. Therefore, in this equation, I substitute x equal to L by 2. Then finally, I got y max equal to minus 5 WL cube by 384 EI. This is the maximum deflection for simply supported beam subjected to UDL. Next, let us see a problem here. A cast iron beam 40 mm wide and 80 mm depth. This is a beam, and the dimensions are 80 mm, 40 mm. Simply supported on a span. It is simply supported on a span of 1.2 meter. The beam carries a point load of 15 km at the center. Find the deflection and take E value. E value is given. So we need to find the deflection, maximum deflection. So we know the formulas for point load. Y max equal to minus WL cube by 48 EI. This is the formula. You can see here. In the previous pages, you can see for point load case. So Y max. Yeah, this formula, if we apply directly, we can do this problem. We can solve this problem. So given that E value is given, length is 1.2 meter, so 1200 mm. B is given, depth is given, breadth is given, load is given, load 15 into 10 cube Newton. So we know that this is everything is given, but I is not given. I equal to, we know that I equal to moment, I is moment of inertia BD cube by 12 for rectangle. So B, D if we substitute, we will get this form. So substituting all the values, W is 15 into 10 cube, L is 1200, length 48, E is given, I we have found out. So we will get Y max equal to minus 2.93 Newton per mm. Y minus indicate the deflection is downwards. Thank you.